Thank you very much for the introduction and for the invitation. It's a great honor to be here and to close the summer school. Well, there will be a workshop tomorrow. So this is a very long slide to start with. We'll speak about set estimation and GPs. There is a list of co-authors of many of the papers I will go through that is too long to be displayed. And also the affiliation, so it's a double affiliation between Idiap Research Institute in Switzerland and Unibern. So before we go and speak about set estimation, I would like to introduce a bit the settings and to maybe go through some stuff that you already know from the other talks on GPs and on Bayesian optimization. So the overall goal, the settings that we will consider here is you have a function f that takes an input x that lives in some space E, and that returns a f of x that lives in some space f. And the game here is going to be to estimate and to quantify uncertainty on some quantities that are depending on the response of this mapping, based solely on the finite number of evaluations of f. Okay, so this is the typical settings. So it's a very, very general setting, actually. So some examples where this arises, first, an example from safety engineering. Imagine that x is a vector that is encoding some physical properties of a system and that quantifies dangerousness. So if f of x, that is a scalar, is large, then you have danger. And if it's low, then it's okay. So in that kind of examples, you're really interested in finding the regions of the parameter space E, where f of x remains low, and finding the regions where it exceeds the threshold, and also locating the boundary between these two subsets. Okay. So another example, another class of examples is to take something higher dimensional, is when you look at flow simulation. So you want to study some aquifer, for instance, and to understand how contamination is taking place in the subsurface. And your x in such setting can stand for properties of the medium, boundary conditions, and f can return something that can be spatial, can be temporal, can be space-time, like the evolution of a fluid over the domain, or maybe some measure of discrepancy between what you observe and what you simulate. So this is a setting that we will illustrate in a moment, where you want, for instance, to recover some contamination source from some observation of a flow at given wells. So let's continue this informal introduction with this typical situation. You have f that was evaluated at a set of points. So the points are instances of your inputs. So this can be points in Euclidean space, it can be functions or media or whatever. And you wish to estimate something that relies on f, and maybe you want to run some new evaluations of f in order to improve this estimation, because this is the big picture. And when you do that, it's legitimate to say that you need a model for f in order to proceed. And you have a number of approaches that exist to approximate a function f based on noiseless or noisy evaluation of f at a few points. So this is basically scatter approximation, or curve fitting, or machine learning, whatever. So here we will exclusively consider the setup of Gaussian process. And the reason for that will become clearer along the talk. But the reason for that is because it's a really cool surrogate model. And it's also because it's not only curve fitting, but it's also coming with prediction uncertainty, and that's quite useful for sequential design. So the idea, as you know, is that we postulate that our function f is actually, which is a deterministic object, is actually one realization of a random object, okay, that we call a random field or a random process. So here the notation Zx means I have a field Z, which is indexed by the location X. And this is a collection of random variables. And now, once you have observed the function f at some points, possibly in noise, you can look at the conditional distribution of the field, knowing the noisy observations. So here you're, just like I think James was pointing, we are precisely saying here I have a random quantity that I'm fixing to a deterministic realization. Okay, so I'm saying this random variable is equal to the value of the function f at point xi plus epsilon I. Then you get a new process, which is a Gaussian process with a conditional distribution given these observations, and you can do a lot of fun stuff with that. In particular, it's very practical for sequential design of experiments because then you have future distribution. If you would have at a point somewhere, then you could speak of the future distribution, and then you can try to guide your search by relying on this future posterior. So the example that comes next illustrates the second point we spoke about earlier. So here we are looking at a flow simulation. So the game here is that we are having a given geology. We are looking at a section of a natural water reservoir called an aquifer. And we assume that at time 0, here there is a contaminant that is spreading in the aquifer. And we are simulating how this happens over the whole domain. And here we are looking at some given locations that stand for wells, for observation wells, and we are measuring the concentration over time. Okay, so we have the quantity of interest is where the contamination started, because, for instance, you want to know who is responsible for pollution. And what you get is some partial information that is just the evolution of the contamination, the contaminant concentration at some given locations. So now the game is assuming I don't know where the pollution is coming from, and I'm just observing these curves, can I find, by using this black box simulation, the location where the contaminant is coming from? Okay? So the brute force approach to that is to say, well, we don't know that this is a starting point, but we can define a kind of search domain, a square. We are in 2 dimensions. We can do a grid, plenty of calculations, run the simulation, compare the curves that we obtain by simulations with the ones that stand for the observation, and then try to find some locations for which the output matches the reference output. Okay? So that's a very naive approach to inverse problems, basically. So let's do that. So here it's not really easy to visualize, but let's get rid of the grid. So the grid's brute force approach is to say, well, let's take this grid, do all the calculations, and what I'm plotting here is actually the misfit, so the integrated error that you have at the observation wells, as a function of the hypothetical location of the contaminant source. Okay? So here is the real location that was used to simulate the contamination. And here is the error, the integrated error that you would have if you would start from another point, look at the curves, integrate the curve, take the squares, and get a number. Okay? So you can see that you have a horrible landscape, completely hectic nonlinear function. And actually, what this plot is telling you is that actually we are lucky. It's identifiable in the sense that if you would find the global minimum of that function, you would actually recover the true location where the contamination started. Okay? So this is really, this calls for Bayesian optimization, right? You see that, you think, wow, we want to do Bayesian optimization there because doing a grid is completely, is super expensive and is simply impossible to perform in higher dimensions. Okay? So here, it's a Bayesian optimization test case example that is following up on the talk of Javier. So now if instead of doing a grid, you take starting space filling design, say the blue points, so you take just 9 evaluations of your simulator instead of around 1,000, a little bit more. And then you do a GP model, you get the standard deviation, predictive standard deviation, and you can look at the expected improvement. And the expected improvement is telling you, well, you should rerun a flow simulation with a starting location for your contaminant that would be here, calculate the misfit, and that would improve, tentatively improve your model and your localization of the global minimum. And then you can do that sequentially. And if you do that sequentially, at every iteration, you're going to run the full flow simulation, calculate the misfit, update the GP model, update the standard deviation, update the expected improvement, and proceed sequentially. And then you see that after about 20 iterations, you have actually located the global minimum. So, yoo-hoo, we have done it. We have an example that is an artificial example that works well with a very standard kernel. Here, there is nothing very fancy. It's just that it's a nice story overall to motivate sequential design based on GPs. And also that could probably be useful on more complicated numerical flow simulations. And I would like to say that first, this example was performed in the framework of a collaboration that is led by Guillaume Pirot from University of Lausanne, also with Tipalo Kritiakiane from Bangkok, and Philippe Renard Neuchâtel. We have a discussion paper, meaning something that is still in discussion on the web, but the data is available. So if you want to play with this function and use that in Bayesian optimization papers, you're welcome to do so. And the main focus today is not on Bayesian optimization, but it's more on a kind of cousin problem, which is I don't necessarily want to find the global optimum of the function, but I want to find regions where the function reaches some levels that are synonymous of danger or something like this. So in particular, well, let's say how to estimate excursion sets and how to refine the estimates in a sequential manner, just like in Bayesian optimization. So before we go there, let me check the time. Yeah, let me just, by passing, recall some seminal references on Bayesian optimization. So probably Javier did that already in his talk, but it's still good to speak about one of the most influential papers dating back to 78. So you see it's already 40 years ago that people started to use Gaussian process priors to fit curves. Then there was this article that is also quite influential in the field of computer experiments, where they have also used some spatial processes, well, GPs basically, to interpolate and approximate computer simulations. These papers here are bridging the gap between spatial statistics and kriging and Bayesian analysis. And this is just one reference among many, because now there is a huge interest on infinite dimensional nonparametrics to show that mathematical statisticians are also looking at GPs and trying to understand what's going on. About GP-based optimization, also the first references date back to long time ago. So in this paper here in 64, they already used some stochastic process prior to perform optimization. The Mokus is probably one of the most influential pioneers of Bayesian optimization, or together with Gilinskas and others. This is also an applied probability paper around this topic, and one of the most cited paper in the area that was published in '98, and they have revived this whole category of algorithms, implemented it in higher dimensional context, and also illustrated that on realistic test cases. So Matt Schonlow was a PhD student. It was just around the time of his PhD or a little bit after. Welch is a professor in statistics, and Don Jones is at General Motors. Okay, so now we leave the world of Bayesian optimization for the whole talk, actually. And we consider another class of problems, but you will see there are many common points, which can be formalized as follows. So for the rest of the talk, we will be interested in estimating not a point, not a value, but a set. And the set of interest will typically be of the form gamma star is equal to those inputs for which the response of the system lies in some prescribed range. Okay? So the response can be multivariate. Most of the time it will be univariate. And the sets that we are considering are typically measurable sets and so on, but I did not bother with too much mathematical details here. And what examples of this that falls under this umbrella include contour lines. So contour lines is the case where T is just one number, a singleton. Excursion and sojourn sets, that will be our main setup. It also relates to admissible regions in constraint optimization, regions of high gradients or high curvatures, and in some sense to Pareto sets in multi-objective optimization, but it's slightly more complicated because then the set capital T depends on the function itself. So we will not tackle that today. So today we will, for simplicity, most of the time assume that the set of interest for the output is a half line of the form T plus infinity or minus infinity T, meaning I want to find those X for which the response exceeds a threshold or remains below a threshold. And we will denote, call gamma star the excursion set of the function f above T. So our aim is to estimate gamma star. What does it mean to estimate a set? Something that is not completely trivial. To quantify uncertainty on it, it's also something that is not completely trivial. In the case where f can be only evaluated at a few points, either in the static case where you have the observations that are there, or where you do observations sequentially. Okay, so coming back to a slide that is difficult to visualize. Here we have a function that is coming from nuclear safety. It's extracted from the PhD thesis of Clément Chevalier, who defended 5 years ago. And even if you don't see the contour lines properly, you can see that there are two regions. A region where you have black area or dark gray area, and a region that is light or white. And actually these two regions, they correspond with responses that are above, so here it's above 1 or above 0.95, and here it's below. And the reason why it's so important in this application to understand where this region is and where this region is because we are quantifying nuclear related danger, which is in that case related to storage of plutonium, so fissile material that you want to store, and depending on two parameters that are here related to the mass and the concentration of plutonium inside of a device, you have a neutronic criticality safety coefficient that indicates a neutronic reaction that either is stable, is collapsing, or is diverging. Okay? So here we are in the region where the neutronic reaction is diverging, meaning explosion, potentially. So for people that are working at Nuclear Safety Institute, like our co-authors, it's paramount to avoid this region. Okay? They want to store nuclear fissile materials. They want to be sure that whatever uncertainty they might have on the physical conditions, they are never going to be inside of this white region. So the problem is that if you knew this function in advance, then it would be just a problem of mathematical analysis. But this function here stands for a very complicated function that requires neutronic simulations. So every evaluation here, an evaluation is a blue triangle, requires hours of calculation. Okay? So you want to calculate this function at a point, you need to run a simulation and wait. That the Monte Carlo neutronic simulator has delivered an outcome that is typically a little bit noisy as well. And imagine now that you're in the situation where you have only observed this function at 6 points, which is a completely crazy situation. Okay? It's not reasonable at all. Okay? So you want to say something about this region knowing the 6 points. So this is the setting, more or less. So we want to estimate the region knowing 6 points, and then we want to add new points in order to better estimate it. Okay, so this is it. Gamma star, you have f of xn that is known, And of course, you need to make assumptions. The assumptions we're going to make are Gaussian process assumptions, which, as you know, is characterized by a mean and by a covariance kernel. And then the fun stuff is that, from a probabilistic point of view, is that if you remember what was gamma star, and now you write it again, but instead of putting f of x, which is the deterministic but unknown quantity, you put z, which is the Gaussian process, then this guy becomes a random set. Okay? So the Gaussian process is a stochastic process. It's a random object. So now the set of points of inputs where you exceed the threshold becomes itself random. And it's actually here a random closed set, provided the set T is closed and the Gaussian process has continuous path. So Dario-Ardimonti made connections to probability theory in his thesis on the topic. Now we'll just, by simulation, illustrate this notion and ask you some questions about that. So remember the test case, right? We have 6 points, and we will assume that we have a GP prior. Okay, so it's given, the kernel is given, the mean is given. It's going to be a Matern kernel, and the mean is going to be 0, I guess. And now you can simulate the GP. You can take samples from the GP. So let's take a first sample. Here we take a first sample, and we truncate the sample. When is the sample exceeding the threshold? And we find this region here. Okay, so this guy is basically a realization of the excursion set. And now you can do it again and again. Okay, because you have a stochastic object, provided you can do sampling, you can look at the possible realization of the excursion set under the Gaussian process prior. And you see that you have a collection of sets that move and which change location, topology, extension, okay? And that induces a lot of uncertainty in many ways, because it's not so easy to speak about the mean and the variance of a set if you think about it. So you need to revise all your notions of uncertainty and of estimator. So we are not, of course, at the beginning of this story of quantifying uncertainties on sets and estimating them, but we are trying to make connections and basically to have the ideas from the theory of random sets being applied, valorized, and investigated in the framework of GPs and computer experiments. So first, some references. So the theory of random sets. It's a very nice book by Professor Ilya Molchanov, who was actually the co-supervisor of Dario-Ardimonti. And then we published this article that will not be the topic of today's talk, but it's closely related about several ways you can quantify uncertainties on sets using GPs in 2016. So now, before we go to something that is a bit more ambitious, let's reduce our ambition for a moment and say it's very complicated to work with sets, but there are many things we know how to do with numbers and with vectors. So let's scalarize the problem. For a second, let us say that we content ourselves with the volume of the set. So we take a measure, typically a Lebesgue measure here, and we say that in order to learn the set, we want to reduce the uncertainty on the volume. So the first question that arises is, what is the distribution of the volume of the excursion set under the GP prior? And this question seems trivial, but to the best of my knowledge, it's not so easy to find an answer to it. So let's review some basic bricks that we will use to better understand this problem. Remember that the equations of GP regression or Kriging are simple equations that are written in terms of the covariance kernel, covariance vector, covariance matrices that you invert, here observations, subtract the mean. Here you have the predictive variance. Okay, so you remember this. And the notations here, Mn, means that you are looking at the predictive mean when you have n observations. Okay, and here this is the standard deviation S. The S square is the variance, knowing that you have n observations. So, for instance, you have the posterior mean here, and here you have the posterior variance of our simple example. Then from there, you can calculate something that is super trivial, which is just the probability of being in the set at any point. So if you take a point x, and you define Pn of x as being the probability for the point to be in the random set gamma. So it's a bit counterintuitive because we are looking at the probability of a deterministic object to be in a random object. But actually, if you think about it, it's just the fact that the process is exceeding t. So then you boil it down to something you know, and that's easy to calculate. Okay? It's just the CDF of the Gaussian with a proper renormalization. So you can calculate this guy at every point. Assuming you believe your Gaussian process, then you know that at every point you have the probability of being in the set that is given by this formula. You can calculate it. And there you get that. Okay? You get that around this point that is actually in excursion, you have a very high probability of being in excursion. Those points here turn out to be a response that is lower than a threshold. So around them, you have a low probability of being in the excursion. You see that it's all very model dependent because it depends on our covariance kernel. And then from there, you can actually do something relatively cool. You can calculate the expected volume. So it has a name. If you say that alpha star is the volume of gamma star, so take the Lebesgue measure of the set, and you call it the volume of excursion, then there is the following property that is super simple, but it's called the Robin's theorem, that tells you that the expectation at time n, knowing an observation of the volume of excursion, is something you can calculate analytically, or semi-analytically, by using the Fubini theorem. So here you have an expectation which is an integral over omega, and here you're looking at the measure of gamma, and the measure of gamma is none other but the integral of the indicator function of gamma over the domain. So you have an integral over omega, an integral over the domain. You can swap them. There is no technical problem here. Pn is remaining between 0 and 1. And you end up with the integral of the probability of being in the set, which is the coverage probability of excursion. Okay? So if you integrate this guy here, you sum all the values over the domain, you end up with the expected measure of your excursion set. So far so good. Now, if you want more than the expectation, and you want the distribution, what is the probability distribution of the volume? I want to know if my dangerous region is going to be 10 square kilometers plus minus something. Okay? I want to know the distribution of that guy. Well, square kilometers for the nuclear test case would not apply. But, it turns out that this is an open problem. Or if it's not an open problem, we haven't found it yet. We haven't found the answer yet. Okay? So these are two references that really state we don't know what is the distribution of the volume. But if you use this trick again on powers of the volume, then you have something really cool that comes up, which is that if you take a power of the volume, so it's basically a moment of the volume, you have the integral to the power r, and then you can say that the integral to the power r by using mute variables is just the integral where you use a notation u1 times the integral where you use a notation u2 times the integral where you use a notation ur, and then you end up with a multiple integral. And this multiple integral, if you swap it with the expectation, you end up with the expectation of a product of indicator functions, which is none other but the product with the expectation of another indicator, which is a probability. So the expectation of this product of indicator is a probability that you're in excursion simultaneously at all the points, and that you integrate over the product domain. So you can, it's not really a closed form formula, but there is a link between the moments of the volume and the probability, the joint probability of being in excursion at all arbitrary points. So if you're able to calculate that guy and to integrate it, then you can get any moment you want. So if you can get any moment you want, you know the distribution. Yes?
Would you mind explaining quickly, maybe explain what a measure is for someone who...
let's say for the moment that you calculate the volume, so here the surface or the volume of the set of interest, okay? And that if you want, you can weight it. So instead of putting the same weight on every square of the room, you can have some regions that have more weight than others when you calculate the total. So that would be a change of measure. That would just mean that you would have a density in your integral. And then you have measures that do not write like that, but it's a bit out of scope. Anyway, so don't freak out because of this. Think of the volume. For the talk, you don't need, it's just a kind of generalized way of writing things where sometimes we need to be careful because we need to make assumptions in order to make sure that everything makes sense. But here, let's think of the volume of the measure as just a regular Lebesgue measure, which is measuring the length in dimension 1, the surface in dimension 2, the volume in dimension 3. Okay? So, do you know how to calculate this guy? Well, it's a multivariate CDF. A multivariate Gaussian CDF looks like super easy, but actually it's not so easy to calculate. Okay? So it's quantity that is for which there are algorithms. There is no analytical form. There is actually no analytical form in dimension 1 already. Okay? So typically when you call the Gaussian CDF on your computer, there is an algorithm, or there is an abacus, or there is something like that. But so for dimension 2, there are super fast algorithms. For dimension up to 20, there are very fast algorithms. And then when you go higher and higher and higher, it gets more tricky. And around 1,000 is kind of the state of the art. There are some algorithms that go beyond 1,000 and that don't take, well, unreasonable times. But it's the limit of current knowledge or, well, algorithmic development. So, in particular, let's come back to Earth. In particular, if you think of the second moment and of the centered moment, like the variance, then you can see that the variance of the volume boils down to something you can calculate. But in the first stage, we did not realize that you could calculate it, so we bounded it. And we bounded it by something really nice. By Cauchy-Schwarz, you can work out the following bound, that the variance of the volume is bounded by the square of the measure of the domain, which is something we don't really care about here, times the expectation of the following integral. And if you take the expectation inside, you end up with the function p, so which is the probability of being an excursion, times 1 minus p. And p times 1 minus p, if you remember the Bernoulli random variables, this is the variance of a Bernoulli. Okay? So flip a coin, probability p of having head, then the variance is p times 1 minus p. So here we are just integrating the variance of the indicator function that says below or above the threshold at every point. Okay? And this is a bound on this. So if we want to set, if we manage to make that guy small, we are going to make that guy small. So this is just a detail, but this is going to be used next. Okay, so now I'm done with this maybe a bit obscure detour, and I will present you some very general setup that you might probably like, and you might probably find some relevant application in your domains, which is called stepwise uncertainty reduction. So I will be very informal, and then I will give you some examples and point you to some literature if you're interested in the mathematical details. It can get very mathematical. Here it's going to be more the global ideas. So we consider what we call the one-step look-ahead strategies. Maybe Javier talked about the multiple-step look-ahead problem in Bayesian optimization. Here we are myopic. We just care about the next step. Okay? And what we want to do is to reduce uncertainty. What uncertainty means is something completely arbitrary. Okay? So this is really what's cool about what I'm going to present, is that you can define uncertainty in the way you want. There are slight technical hypotheses, but it's very broad. Okay? So for instance, you can say my uncertainty is the integral of the variance. I measure the uncertainty of my GP by saying if the integral of the variance is small, then I have small uncertainty. You can say is the variance of the volume. Okay, I'm looking at the excursion set problem and I'm interested in the variance of the volume, and I can say this is my measure, my number that quantifies my uncertainty, or that expresses what I conceive as my main uncertainty. So you call it Hn. And what is Hn? It's a function. It's a random variable that writes as a function of the probability distribution of your field at time n. So of your Gaussian process at time n. So you have n observations that gives you a posterior distribution for your GP. This posterior distribution is a very, very broad object. Okay, it's a random function. It has a mean, it has a covariance. And then you derive something which is a random quantity which depends deterministically on the distribution of your field. It becomes a random quantity because it depends on the observations that are treated as random. So imagine that you have n naught points and that at every iteration you're going to add a new point, x star n plus 1, in a way that you minimize the future uncertainty. So you have a notion of uncertainty that is relying on n plus 1 observations, but so far you have only n observations, so you anticipate what will be the uncertainty at the next step. And this uncertainty at the next step depends on where you will make your next measurements or your next observations. Okay? So xn plus 1 here is where you will put your next evaluation. Xn plus 1 is your future uncertainty, that is a random variable, but you take the expectation of this random variable at step n. So you just account for the observations that you have now. Okay? And then you want to minimize this guy. So it's just like expected improvement, but it's in a much more general fashion, because you can look for many other goals. So this is an idea that has been in the air for several decades, but there is, in this setup of GPs and sequential design of experiments, I think it's fairly well presented in this paper that was published in 2012, if you're interested. And here let's have a deeper look at what happens in the case of two uncertainties. One is the variance of the excursion volume, and the other one is the bound. So we say that we measure the uncertainty by integrating Pn times 1 minus Pn, which is the variance of the indicator function of being inside or outside the excursion domain. Okay? So these are the two ones that we have looked at primarily during the PhD thesis of Clément Chevalier. And so the uncertainties that you have here are there, and the corresponding stepwise uncertainty reduction criteria are just expectation of the future value of those guys, assuming I add a point. So here it's not xn plus 1, it's x. It's a mute variable anyway. And so basically, if you can calculate those guys, then you have a way to perform just like Bayesian optimization, but to solve other classes of problems. So at the beginning, when we looked at that, we were like, oh, is it really possible to calculate this? And then after a while, we ended up little by little finding analytical formula or semi-analytical formulas for quantities arising in this criteria. So there was a paper in Technometrics in 14 presenting this, and also a batch sequential version of that, and also a package called Kriginv, and there is a paper, a tutorial paper that 2014 that presents this kind of criteria and how you can use them, maximize them, and how our codes are working. So let me give you an illustration, okay, before going deeper into random sets. So now we come back to the nuclear safety problem. We have the 6 points, and here we have Pn. Pn is the probability at any point to be in the set. And there you have here the real boundary between excursion and non-excursion. What you see here is just like expected improvement, but for the decreasing volume. So here it's not really the volume, it's the H tilde, so it's the criterion that tells you at any point of space what would be your future uncertainty if you would add a point there. Okay? Future expected uncertainty. So the criterion tells you should better put a point around there. So then you do that, okay, and putting this point is going to reduce a lot the uncertainty in the sense that you had a lot of gray regions where you were not really able to know whether you're in excursion or not, and now you see that you have more black and white regions, and the regions where you're not very confident or shrinking, and you are next invited to visit around there, and then you can do that sequentially, and what happens is that you will progressively visit the contour and decrease the regions where Pn is far from 0 and 1, which means that Pn is around 1/2, for instance, which means that Pn times 1 minus Pn is large. Okay? So you would like this P times 1 minus P to be small, meaning it's either close to 0 or close to 1. So this is what happens. Okay? So now just another illustration. Up. With the batch sequential, you can also do that 4x4 or 6x6 or whatever, if you have a way to parallelize your simulations. So here, the points are added 4 at a time, and you see that 3 iterations of batches of 4 are doing the job properly. Again, this is all on a simple test case in 2D with a kernel, a function that is simple, a kernel that works okay, and we should not generalize these successes too far, right?
Do you optimize kernel parameters?
Yeah, here they are estimated, which makes the theoretical analysis complicated, actually. Our results are generally at fixed covariance kernels. Here they are re-estimated. Yeah. Sure, sure.
Would you also want to kind of sometimes explore a little bit? Because maybe you don't know up on the top you don't have much samples, so maybe you're above threshold over there as well.
So it's a very good point, and actually it addresses well my comment on the model misspecification. If you're model believer, then what we do is optimal in the one-step look-ahead sense. So it's optimal assuming that your next evaluation is going to be the last one. If you would do something that takes into account the fact that you have a budget of 20, then you would probably be more exploratory, and you would address your comment in some part. Plus, if you believe that your model might be crap, then it's probably good to alternate between a more geometrical exploration of space and model believer exploration. So, good comment. So, this work started about 10 years ago. Well, from my side, at least. Some people had done work on similar related topics before, and it took us around 10 years to understand the theory. So first we have had the intuition that, well, we could do something that does a little bit like expected improvement, but for this problem, the nuclear safety people were really interested in that, and they have fostered it. And along the years, and speaking also with other colleagues, well, Julien was already involved in many things on the excursion set estimation side. François Bachok recently joined the team with fresh ideas, also from a very theoretical point of view. So these two guys are quite theoretical when they want. And we have been able to establish a broad category of results under the assumption that the covariance parameters are fixed and that the functions are actually generated from the GPs, that this class of sequential uncertainty reduction or stepwise uncertainty reduction strategies converge, in the sense that if you wait forever, you're going to have your uncertainty decrease to 0. Okay? Which was not for granted, because you have results in the literature that say for expected improvement, for instance, that you can get trapped. So you have some pathological functions where you can spend forever in a region or believe that you have a 0 variance in the regions that you have never explored and then never explore it, which is not the case here, but not for specific pathological test cases with probability 1 under the model. So it's different class of results, but that address also expected improvement concerns to some extent. Okay? So for those of you who are interested in theory, I really invite you to look at this paper that is not yet accepted, but hopefully soon. And now I'm coming to the probably final topic of the talk, which is, well, remember I said at the beginning, well, set estimation is complicated. You don't really have expectation and variance. And then I cheated, because then I boiled down to the volume. And then we did plenty of things with expectation and variances. But now let's come back to the harder problem. I want to estimate the set, and not only its measure, not only its volume. So how can you do that? So it's a very broad topic, and I will just present one angle to that. So you fix n. You want to estimate gamma star, which is the actual set, and you want to come up with a representation of variability and some corresponding estimates. So now for a moment, we will change the perspective. For technical reasons, we will consider the case where we want to recover the white set. No, the dark set, which is the region that is safe. Okay? So we want to estimate gamma, which is where z of x is below t. And we call Pn the probability at every point for the response to be below t. And now we will play with a notion. Probably most of you know what a quantile is. So here we will play with the notion of quantiles for sets. So what is a quantile of a random set? So here we're going to consider the function Pn that is giving you at every point the probability of being in the set. Okay? So here, you remember this is the safe region. So here you have a very high probability of being in the safe region. Here you have a small probability of being in the safe region. And now what you can do to estimate the set is a very, very intuitive idea, basic idea. You can take this probability and just truncate it. You can just say those regions of space where the probability of being in the set is sufficiently high, I consider that they are in my estimate. And those that have small probability, I get rid of them. Okay? So we're going to truncate this function here. Look at the level sets with level rho, and that gives us a family of sets. So it's basically you have the level of the response go up and down, and that gives you a family of sets. Okay? And you want to find the rho, so the level where you truncate, that is optimal. Optimal in what way? So optimal in a way that you want that the measure, so again, the measure comes back, you want that the measure of the symmetric difference between your estimated set, Q rho, and the actual random set is as small as possible in expectation. Okay, maybe I can draw a picture. So you have your, well, you have your random set, and you have an estimate of it, Q rho, and this guy, gamma, you have to imagine that it's moving around. Okay? Gamma is moving around. But what you can do is formally you can speak about the symmetric difference between gamma and Q rho. That would be those points that are in gamma but not in Q rho, and those points that are in Q rho and not in gamma. And then you can measure the surface of the hashed region. And you can say, well, this is a random quantity because gamma is random, but I can try to find rho such that this quantity, the expectation of that surface here, is going to be minimal. Okay? And it's a nice result that you can find it. It's possible to find the optimal rho. So it's called the Vorobyov expectation. So the Vorobyov expectation consists in taking rho star such that, so you see that rho is going to be here. You're looking at the probability of being larger than rho. So if you let rho increase, then the set is going to decrease because you're going to ask more and more and more and more. Okay? So now you have a monotonic function, and actually, most of the time, you can find a rho star, you can cross the rho star such that the measure of Q rho star is equal to the expected measure. And you remember that the expected measure, we know how to calculate it because it's the integral of the coverage probability function. So it's a state-of-the-art result that Q rho star is actually the set that minimizes the expected measure of the distance of the symmetrical difference between this set and the random set gamma among all closed sets with a volume equal to the expectation of mu gamma. So there is an optimality result for this rho star. So here, if you take the rho star corresponding to this problem, it will give you the orange contour line, meaning that those points that are outside of this orange boundary, they are in Q rho star, and those who are inside are outside. So the Vorobyov expectation of the safe set is the points outside of the orange region. But still, there is something that is not completely satisfactory about this concept, because it's clear that you might have points, regions here where the probability of being in the set is really high, points there where it's a little bit lower, like 0.8. But actually, if you're thinking of nuclear safety, you would like to control the probability that all these points are safe. And this is not the same story as controlling the marginal probability for every point to be safe. So you need to speak about the joint probability, but here you have many, many, many points. So we have a complicated problem, and I will now dive into it. So it's hard to make confident statements. So for instance, if you take the level set with 95%, so here I'm just truncating, looking at those points that have a probability of being safe that is higher than 95%, which gives me two components here, okay? Two connected components. If I calculate the probability that all the points in this estimator are safe, I get 67%. Meaning that if I believe that my function is a GP realization, and if I calculate the probability that this whole set, which has been discretized, is below the threshold, then I have only 67% of the realization that pass the test, and 33% for which there is at least one point in this region that is unsafe. If you take 0.5, you have less than 1% of the realizations that will be really safe. And for 56, which is the Vorobyov expectation, you have less than 2% probability that the whole region is safe. So this leads us naturally to the question, is there a way I can design a conservative estimate? So what is a conservative estimate? This is something that you can find, for instance, in the paper by Bolin and Lindgren in Series B 2014. You want to control the probability that the whole set is safe. Okay? So this is the probability that the whole quantile is in the actual safe set with a probability larger than beta, but then that doesn't really define a set. So you want to find an optimal set in the sense that it has the maximal volume. You want to find the largest set such that you have the probability of being safe that is controlled, and larger equal beta. Okay, so then now I'm going to have to rush a bit. So this computation here is super hard because you want to solve a maximization problem of a Q row of rows if you want. So you need to play with one indicator, which is rho, so it's one-dimensional. It's not too bad, but the problem is that the quantity that comes in here is a very high-dimensional CDF. And we said some time ago that the high-dimensional CDFs are super hard to calculate. Okay? So we need to find the set with the maximum volume, and we need at every evaluation of this to calculate the probability of the whole set to be safe. So for that, we have developed a computational framework. So it's called an orthogonal probability, this guy. And we realized that high-dimensional orthogonal probabilities was still a challenge. So we looked at the state of the art and developed some specific Monte Carlo framework to come up with estimates of that in this paper. And here we'll maybe skip the details of our technique that is based on some quadrature points and some reasoning over the remainder outside of the quadrature points. And now come back to the test case. And then I'll finish with a bonus on a new test case we are looking at with a different question. So we come back to our test case, and now we try to come up with an estimate of the safe set. So here is the one we obtained by our technique to get a 99% probability of being safe. So this is the largest volume set that has a probability at least 99% of being safe, given the GP prior. And now we're going to finish the part of the talk, well, the main part of the talk on conservative set estimation and on sequential uncertainty strategies by blending the two ideas. Why not do something sequential where we want to add a point in order to better reduce uncertainty on the conservative estimate? Okay, so this is some ongoing work. So here we are sequentially adding points so that the conservative estimate is going to be better and better in some sense. So either in terms of type 2 error or in terms of volume. And what you see, it's really cool, is that the set, I mean, it's really cool not because of us, by nature, the set is going to be approximated mostly from outside. Okay, so here it's dangerous set. So the white set here is making progress and progress and progress, but in a conservative way. Okay. We are really making all we can not to have any error on that side. We tolerate error on the other side, but we downweight the error, well, we overweight the error here so as to avoid them. We tolerate to miss some dangerous regions. We tolerate to miss some safe regions by flagging them as dangerous, but we don't tolerate to flag a dangerous region as a safe one. Okay? So this is a paper that is in revision at the moment. We don't have any asymptotic results. On the conservative case, it's a bit more complicated, not only because of the parameter estimation. There are some tricks that we use, and probably one perspective is to make it full Bayesian. Here we estimate the covariance parameters, and at every step we treat them as fixed. Yes?
The estimate to optimize the volume of the region by conservative estimated 9%. Is that?
So yeah, I didn't give all the detail, but actually we consider several criteria. One of them is the volume. You want that at the next step, the volume of the future conservative estimate is as large as possible, but under the conservativeness constraint. So that makes it very intricate. But it's possible.
Does it listen to objectives?
You could see that way, yes.
Then so just to try to somehow convert it to one metric.
Yes, you could see that also as a type 1, type 2 error thing. And then you could aggregate the objectives. Yes, yes, absolutely. Okay, so I'm thinking mostly, so the test case is coming from the French Nuclear Safety Institute. So Dr. Yann Richet and Grégory Kaplan provided the test case, and we have had some collaborations over the years. And I really would like to thank Dario Azimonti and Clément Chevalier that have been, well, of whom I've presented a number of PhD works actually throughout the presentation. And I realized that it's too short for the bonus, so I prefer to take questions instead. Thank you.
Possibly a completely bonkers question, but many statistical quantities you might want to estimate can be written in terms of integrals over excursion sets. So like, let's say if you had nested sampling, so you get the marginal evidence percentage to evaluate, for example. Does this kind of has this approach been used to try and answer any kind of questions and so on? Is that a completely stupid question? Does that make any sense?
Well, this is a question that comes again and again, actually. So, yeah, I think these methods could be used, provided you can model a likelihood or log likelihood or some derivative of the log likelihood with a GP, whatever.
Yeah.
Yes, probably it could be interesting to use those techniques to locate plausible regions. And this is what Ian Vernon is doing in calibration, right? Also with discarding some unlikely regions.
So, for example, for nested sampling, the trick is you convert a multi-dimensional integral into a one-dimensional integral,
Yeah.
where you integrate the excursion volume.
Yes, yes, yes. So there is, I'm not completely sure it addresses your question, but there is another paper by Becht and Vasquez and Lee on Bayesian BSS. It's a Bayesian subset simulation. Where they are having this annealing thing, right? Where they are trying to calculate the measure of rare events. And there they are doing something sequential where the GP is instrumental over the iterations.
Okay.
See? So that's probably addresses to some extent your question.
Well, I think subset simulation is a key part of meta sampling. It probably is.
Yes.